Hi, everyone. Let's talk about 5.4. This section focuses on trigonometric functions of real numbers. Let's go back to what radian means in a circle. So last week in section 5.1, we learned that theta is equal to S over R, where S is arc length. It's how long the rim of the circle, this distance outside. I guess if I were to trace that, it's this length. I'm not tracing it very well, am I? It's this length right here. It depends on your angle in radians. And if we took S and divided by R, which is the radius, that will give you the measure of radians. In a unit circle, which we're going to focus on today, R is 1. So if we take the formula of the radian and take S divided by R and replace R with 1 and say theta is S over 1, we have theta equaling R. So in a unit circle, the radian measure of the central angle is equal to the length of the intercepted arc, which is the S. S is your intercepted arc. So this only applies to the unit circle. So for unit circle, we go back to our definition from 5.3. If your circle is drawn like this on a coordinate plane, and you're starting at the center, 0, 0, and we have a unit circle 1, and we're going to have a point P labeling with A, B, and find that we have this point P. Actually, let's just follow regular XY. Let's make that XY instead of AB. So our point, we're just going to call XY instead of AB so that we know which coordinate we're referring to. And let me make a triangle straight down. So here's our triangle. In a unit circle, instead of calling the angle theta, we call the angle T. So this is T. And here's our triangle. So in that case, if we have our triangle, our adjacent side, we label X, our opposite side, we label Y, and our radius is 1. So within a unit circle, sine T is opposite Y over hypotenuse 1. And Y divided by 1 is just Y. So we're going to just say this is Y. Cosine of T, where T is the angle and the reference angle in the unit circle, is adjacent over hypotenuse, adjacent being X, hypotenuse being 1, and X over 1, we all know that's just X. Tangent T is opposite over adjacent. So in this case, opposite is Y, adjacent is X. Let's go to the reciprocal functions. So the reciprocal of sine is cosecant T, and that's the reciprocal. It's 1 over Y, assuming that Y is not equal to 0 because we can't divide by 0. The reciprocal of cosine is secant, secant T. So secant T is 1 over X, assuming we X is not 0. The reciprocal of tangent is cotangent T. A lot of people like to pronounce this as cot, but I want you to say the full thing, cotangent. And it's the reciprocal, so it's X over Y, assuming that Y is not 0. Okay, so make sure that you do have this in your notes so you can refer to it as you're doing the homework for the week. Oh, and I forgot to mention, of course, the radius, since it's 1, right? X squared plus y squared is equal to r squared, but since radius is 1, we have x squared plus y squared is equal to 1. Okay, let's look at the sine and cosine functions. Just take a moment to focus on just these two functions. We are going to look into graphing these next week. And if we do graph them, these are really cool in that like it's a cyclic function where it looks like a wave and it keeps going. If I were to continue this, the sine graph right here, this would keep going and going and going without any limits. It just continues to the right towards all the positive x values and continues left. And the same for cosine. They look very, very similar, except you see at 0, cosine starts up here and sine starts down here. So these are the two trig functions. They're defined for all real numbers. And the sine function and the cosine function are such functions. The domain, which means how far to the left and how far to the right does this go, is negative infinity to infinity. And look at these functions and see how high does it go up for the y value. Well, if you look at the sine function, it does not go past 1. And it does not go below -1. So it kind of oscillates, bounces back and forth between all the values of -1 and 1. And same thing for cosine. It oscillates between 1 and -1, never goes past 1, like never goes higher than that, and never goes below -1. So the largest possible value for the sine function and the cosine function is 1. And the smallest value is -1. And the range, so therefore, is bracket -1 to 1. And we'll get more practice this on the domain, range, and graphing next week. Okay, so let's actually do a problem. So let's take a look at this graph. We already have a circle, a unit circle. And you see how instead of using theta, we're using t. That tells me that we're working with the unit circle with the radius 1. And the point that it's at is -1/2, -3/2. So let me just go ahead and label this r is equal to 1. So let's find the values of trig functions at t. So let's start with sine of t. We just filled out that chart that sine of t is equal to the y value. Well, here's the y value, x value and the y value. The y value is -√3/2, done. Right? We didn't have to divide because it's just dividing by 1. So it's just, you just take the y value. Cosine of t is the x value, which is in this case just -1/2. Done. Tangent of t takes y and divides it by x. Y in this case, it's -√3/2. X is -1/2. With fractions, it means that you multiply the top by the reciprocal of the bottom. And so here the 2 would cancel, and 2 negatives make a positive, so we have √3. Okay, let's go on to do the reciprocal functions. The reciprocal of sine is, maybe I'll do it up here. Actually, I'll just stay down here. Cosecant t, where we take 1 and divide by y, which just means you take whatever you got for sine and you flip that over, getting -2/√3. Let's do the rationalizing of the radical to multiply the top and the bottom, right? √3. So we get -2/√3 over square root of 3 times square root of 3 is square root of 9, which simplifies to 3. So there's cosecant, -2/√3/3. Let's go on to the secant t. Secant t is 1/x, and 1/x is 1/(-1/2). The reciprocal of -1/2 is -2. Last but not least, we have the cotangent function. Cotangent is x over y. X in this case is -1/2. I'll try my best to squeeze this. And then y is -√3/2, which means I take the top, multiply by the reciprocal of the bottom, -2√3. It cancels the 2's, negative makes it positive, so I end up having 1√3. We're going to rationalize because my math lab does not like radicals in the answer. So √3 over √3, so we get √3 over 3. So there is the cotangent. Right, these should be much easier than the problem we did in 5.3, because 5.3, the radius was actually something different, but with unit circles, the radius is 1. And so it's really easy to find the 6 trig functions. Okay. The next thing I wanted to do with you is to use the unit circle to find the values. We started doing some of this in 5.3, where we use unit circle to evaluate values. So I'm just going to focus on the radian measure instead of degree measure. And so when you see sine of 0, it doesn't have the degree symbol, so you assume that it's a radian. So sine of 0 radians. So we look at the unit circle. And again, you have access to the unit circle. I did upload a PDF file of this. We look at the unit circle and we're looking at, grab the highlighter, 0 radians. And with sine, remember that this is equal to the y value. So I'm going to see what is a y value at 0 radians? Well, it's 0. The y value is 0. So the sine of 0 is just 0. Let's focus on sine of 5 pi over 3. Well, sine of 5 pi over 3 is, there it is, 5 pi over 3. What is the y value of that? Well, the y value is -√3/2. So there it is. I did get questions about like where to place negatives in the answer. You could place the negative with the top number with fractions. You could put it in the bottom, or you could just put it all the way in the front of the fraction. I usually do the top or the side. It's, I mean, this is not wrong to put it at the bottom, that's okay, but usually we tend not to put negative signs in the bottom of the fraction. So just keep that in mind. I did have some questions about that. Okay, let's look at cosecant. Remember, cosecant is 1 over y. So at 5 pi over 3, I'm going to take 1 and divide by the y value, -√3/2, which just means we take the bottom. 1 divided by that fraction is the reciprocal. So it's -√3, -2 over √3. And by now, you should know that we need to rationalize, can't have radicals in the denominator. So let's multiply this by √3/3, giving us -2√3/3. Right, taking a look, we just box our answers here. At the last one, 21 pi over 4. Now look hard, you're not going to find 21 pi over 4 in the unit circle because the unit circle only goes up to 2 pi, right? 0 and goes all the way around. Actually, I should write 2 pi here and goes back to 2 pi. 21 over 4 is much bigger than 2 pi. So actually, I'm going to head over to my calculator and make my calculator do the work for me when I can. And so it's 21 pi over 4. Again, you have to keep subtracting 2. You're kind of rewinding the unit circle until it gets on the unit circle. And so that's 3.25. Subtract it one more time. And you're subtracting until you get something lower than 2. 3.25 was still too big, still bigger than 2. I'm going to do it one more time at 1.25. Let's change that to a fraction. We have 5 over 4. Okay, so I know 21 pi over 4 is equivalent to 5 pi over 4. So let's go back to our slides here. So this is equivalent to sine of 5 pi over 4. And if we look at 5 pi over 4, the y value is negative 2 root 2 over 2. And that is our solution there. Okay, let's try the next ones. All right, so same concept, but this time I want to focus on cosine and secant. So cosine of 5 pi over 6, you want to see what's the x value at that angle measure. So 5 pi over 6 is, there it is. And if I look at the x value of that coordinate, it's negative root 3 over 2. Okay, negative 5 pi over 6, because it's negative, we have to find the angle that's equivalent to that negative angle measure. And to do that, we have did some of these problems last time, where we have to add 2 pi. Of course, your calculator does that for you easily, so let's do that. So we have negative 5 over 6, adding 2. Let's change that to a fraction. So 7 over 6. Okay, so negative 5 pi over 6 is equivalent to 7 pi over 6. So let's look and see, where is 7 pi over 6? Oh, it's down here. The x value of that angle is negative root 3 over 2. Oh, so it's actually the same as 5 pi over 6. All right, so the 21 pi over 4, again, that's way too big. I think, was this the same one that we did before? We did sine of 21 pi over 4 is equivalent to 5 pi over 4. So here, cosine of 21 pi over 4 is equivalent to cosine of 5 pi over 4. Let's see where 5 pi over 4 is. 5 pi over 4 is down here. The x value is negative root 2 over 2. Okay, so you can see cosine. You locate the angle and you just report the x coordinate on the unit circle. Let's go to do secant of 4 pi over 3. Secant is 1 over x. So we locate 4 pi over 3. There's the x value. So we have to take 1, divide that by negative 1 over 2, which means we do the reciprocal of the bottom, which is negative 2 over 1, which is just negative 2. Secant of 3 pi over 2 is, again, 1 over x. So 3 pi over 2 is right here. And that's 1 over 0. And, oh, sorry, it's negative 1 over. No, it is 1 over 0 because the x value is 0. 1 divided by 0 is undefined. So secant of 3 pi over 2 is actually undefined. You may wonder, can we do these on a calculator? I mean, you certainly can. Let me show you, though, that the calculator won't give you exact answer for the graphing part. I mean, the graphing calculator. So let's just take the first example of cosine. Oh, let's go to mode, make sure we're in radian mode because we're dealing with pi. So something like, let's see, cosine of 5 pi over 6. Okay, it's going to give us a decimal because remember we got the answer negative root 3 over 2. I'm just going to do this, oops. Negative root 3 over 2 and show you that it's equivalent. The only downside is it gives it to you in a decimal and not the root form. So you would have to do the root form by using this unit circle. Now, on the other hand, if we had something like secant of 4 pi over 3, remember secant is 1 over cosine. So I would put that in as 1 over, because we don't have a secant button, so we have to use the reciprocal identities. 1 over cosine of 4 pi over 3. Remember the answer to that we got as -2. So like if we had whole numbers or nice fractions, you could double confirm your answer by putting it in, but with answers with roots or radicals in them, it gives you the decimal form of the answer so that you could check whether your answer is correct by comparing the radical form of your answer in decimal, but it won't give you the radical form. All right, let's look at, but I know there are other scientific calculators that do that, but not the graphing calculator. Okay, going back, we just got 3. So let's look at 4. I'm focusing on the tangent and cotangent. So tangent is y over x. So whatever you get for the y, you're going to divide by the x. Tangent of pi over 6 is, there's the angle. And there's my x value, there's my y value. So we're going to take 1/2, divide by √3 over 2. And take the top, multiply by the bottom of the reciprocal, which is 2 over √3. The 2 cancels out. We get 1 over √3. We got to rationalize. So 1 over √3, multiply that by √3 over √3, giving us √3 over 3. So tangent of pi over 6 is equal, it's equal to √3 over 3. Let's look at tangent of pi over 2. Pi over 2 is here. And taking again y over x. So x is 0, y is 1. So we're taking 1 divided by 0, which is undefined. Tangent of negative pi, again with negative, just add 2 pi. -1 pi plus 2 pi is pi. So this is actually equivalent to tangent of pi. Tangent of pi. Okay, let's take x or y, divide by x. Y is 0, we divide by -1. And so that's just 0. Okay, you can divide 0 by something, but you can't divide by 0. Okay, tangent of 2 pi. 2 pi is equivalent to 0. So 0 and 2 pi, they're equivalent. And we take the x value, the y value, take the y value 0, divide by 1. So it's 0 again. Cotangent of 5 pi. 5 pi, again, way too big, but if we keep subtracting 2 pi until it's something lower than 2 pi, we get 1 pi. So cotangent of 5 pi is the same thing as cotangent of pi. Cotangent of pi, and cotangent takes x and divides y. So here's x, here's y. X is -1, y is 0. Again, we can't divide by 0, so it's undefined. All right, let's go on to the last problem, number 5. So sine cosine functions are used to model things that behave in like a cyclic manner, like a wave function. So here we have the number of hours of daylight. We're saying that's h on day t, and t is any given year, where if it's January 1st, is t is equal to 1. So I guess the last day on the calendar would be t, it would be 365. And this is in Fairbanks, Alaska, modeled by this function, h of t equals 12 plus 8.3 sine of big bracket 2 pi over 365 times t minus 80. Because we're dealing with pi, when we do this problem, we want to make sure that our calculator is in radian mode. So part A says June 21st, the 172nd day of the year is the summer solstice, the day with the maximum number of hours of daylight. Let's find the number of hours of daylight in Fairbanks on this day, and we want to make sure to include units and round to the nearest tenth of an hour. So for this, we just need to substitute our value for t. It is giving us t as 172. So we're going to plug that in. We're trying to solve for the number of hours, so h of 172. So we got to plug that into the function. 12 plus 8.3 sine 2 pi of 365. Putting 172 minus 80, close, big bracket. So let's put that in the calculator. I'm just making sure that we're in radian mode, and we are. So we have sine, or no, actually we start with 12. Let me just clear all this out. 12 plus 8.3 sine of 2 pi over 365. Another, actually, yeah, another bracket. 172 minus 80. Close that inside bracket, and then we need an outside bracket. Okay, so we're getting 20.299. And this problem wants us to round to the nearest tenth of an hour. So we have 20.3. And to include the units, it's the number of hours. So during the longest summer day in Alaska, they get 20.3 hours of daylight. So I've never been to Alaska, but I hear that sometimes their nights are super short, so they have to close the curtain like really with dark blinds to get sleep. Okay, let's look at the second problem. December 21st, the 355th day of the year, that's the winter solstice. That's their day of the minimum, or the day with the minimum number of hours of daylight. So let's do the same thing, find the number of hours of daylight, see how short their daylight is on the winter solstice. So here we have 355. And so t, we're going to use t as 355 and put that in. Same thing, 12 plus 8.3 sine. Actually, you guys aren't able to see, so let me forgot to switch over. I apologize. Okay, so we're in the second problem. Where t is 355 for the winter solstice on December 21st. So plugging 355 in to the function again, 12 plus 8.3 sine of 2 pi 365, putting 355 minus 80. Okay, let's put that in the calculator. All right, I'm going to use what I have typed. I'm just going to copy and paste. It's the same function and just change 172 so I don't have to type it all out again. So 355, and we get 3.7019. So rounding that to the tens place, it's 3.7. Make sure that I change back to the slides this time. All right, there we go. So we have 3.7, which is a really short amount of time to get daylight. 3.7 hours. Right, this was a shorter unit. So we're going to wrap it up here. Let me know if you have any questions in the meantime. All right, have a great day.